It's 3 o'clock, so let's get started. So everyone, assignment 3, people turned in. So I figured it'd be a good idea to go over one of the things most people had struggled with, which was the generalized n-queens problem, which I'll pull up one student's submission, which totally worked perfectly. So the main idea here was to do backtracking, obviously. So you start at the first cell, or whatever you determine the first cell to be. Then you place a queen there, if you can. Then you keep scanning for the next one by doing recursion until you find a place where you can place a queen. Then place it there. Then keep going until you can do it again, again, and again, and again, until you're all done. And so the idea here was basically, if you can place, so what this student did was basically loop over the entire grid, which has n squared cells, and you determine if you can place a queen at this particular location x. So instead of representing this as a n by n matrix, the student just represented it as a 1D n squared length list. So you just loop through there. If you can place it there, then basically then you can assign a string to that position saying that you actually could place it there. Then we recursively call ourselves and say if you can solve this by doing it recursively, then we found a solution. But otherwise, then clearly this position must have been wrong, because by placing it here we couldn't solve it. So therefore we have to place it to be blank, and then we backtrack. So that was just the main thing. And then check result is just basically checking the number of queens in a column, row, and each of the 2 diagonals, and making sure that it's at most 1 for every single queen. Okay, so I know the assignment was a little more challenging than I thought because of all the edge cases here, but what I wanted to see was that you were able to think of this as a backtracking problem with using constraint satisfaction, in the sense that you have to make sure that for every queen you place, you have to be able to have at most 1 queen for each of those 3 conditions. Okay? So any questions about this or assignment 3 in general? Yeah.
I have a question, kind of mostly, I guess, with the backtracking. So, say like for this one, you try to place a queen there and realize that, okay, it won't work. So you backtrack to the previous one, the previous spot where you tried to, right?
It's almost that. So I just say, I'm going to place a queen here, then I'm going to recursively call on myself.
Yeah.
If the recursive call says no, then that means that this placing must have been wrong. So I must say that I cannot place a queen here, and then I stop this particular call right here, then I must backtrack in that case.
Okay. How does it tell, say you backtrack to the previous one,
Yeah.
and that one doesn't work?
Then you backtrack again.
Okay. Where, like in this one, where is this code that showing it backtracking?
So, well, the backtracking is when you exhaustively go through the n squared items.
Okay.
Because you're, for other than 2 values, you're guaranteed that that there is a solution. You will hit 1 eventually.
Okay.
It's just that you'll be looping possibly through the entire thing, and so when you finish doing the recursion, then when you're done doing the recursion is when you basically go through this entire list.
Okay.
And it says, like, when I'm done recursion, then I need to check my result and then just return false or true depending on whether this particular call actually worked.
I see.
Yeah. That's the main. So it could say, if it says false, then I'm going to return my caller false. and then therefore it's going to choose the next thing, and then it may say false again, so we backtrack.
Gotcha.
Yeah.
Okay.
So any other questions on assignment 3? Okay. So in light of assignment 3, I extended the due date for assignment 4 to be next Monday instead of this Thursday, which I thought was a little too quick. So the only thing about assignment 4 that's changed was there's a little bit of a small details if you've been working on that. There's a small detail change there because I wrote it wrong and therefore it would give you a wrong solution. But other than that, it's the same as before. Any questions about assignment 4? Okay. Yeah, it's just pretty straightforward. So the main idea I want you to be able to do here is that this is a table that's provided in a paper. I want you to be able to implement a particular strategy for, in this case, n queens that is from a paper. So it's just being able to understand the result of a paper and being able to implement it. Then you'll solve Project Euler 18. We went over that last time. And doing and implementing an algorithm for counting triangles in a graph. Well, we went over that last time. And Project Euler Problem 107, which also has to do with graphs. And if we didn't go over the material for that, so if you are able to solve that, that would be really good. Okay, so that's why I counted it as extra credit. Any other questions on assignment 4? So I just wanted to go over, I haven't posted this yet, so because there's a few things I need to change, but I will soon. And we haven't actually went over all the material for this yet, so that's why I want to wait a little bit. But this is assignment 5. So the main idea behind assignment 5 is that we went over this Facebook data set. So we computed the breadth first search tree and the depth first search tree with that really awesome looking picture with the branches coming out. And what you'll be doing here is you'll be analyzing this data set a little bit more. So we talked about when to use undirected and directed graphs. So undirected means that you can travel in either direction of the edge, it doesn't matter, but directed it does matter. So Facebook, since you're friends with a certain person and they're also friends with you, that makes sense to think of that as an undirected edge, right? But I asked the question here, what if the edges that are described in the data set are actually directed edges? Like, what changes about the graph then? Is it still a strongly connected graph? Because we know, and we verified in class, that this is a connected graph in the undirected form. We know that by definition it's weakly connected, but is it strongly connected? And then I ask you to do the reverse direction as well, instead of just the forward direction for a directed version of the graph. All right. So now I want you to be able to, instead of just looking at the whole graph, find the induced subgraph on vertices of with a particular property. In this case, having degree at least 2, and then I want you to figure out, is the graph still connected? And then if it's not connected, how many components are there? So a component for an undirected graph means that it's just a group of vertices that are all connected. So it may be possible in this part that you'll have a component which is all connected, then another component which is completely separate, then maybe another and another, something like that. You may only have one, you may have many. And so that's what I want you to do that for that part. Then if it just happens that the graph is still connected, I mean it has one connected component, then I want you to change this value of the degree for which you extract vertices and do the induced subgraph thing until you have at least 2 components. So you basically will be filtering out more and more vertices over time until you have 2 separate components. All right, and then an interesting question here is, it could be possible that you have two components and then you keep upping this value of the degree until you get to a certain point where you have only one component and then it breaks off again. So I just want you to be able to verify that, if that's true or not. I'll go over the extra credit in a second. I want you to plot betweenness and closeness centrality values, so we'll go over that today, of the graph, and then use matplotlib to do a plot of that. So like we did in class with the degrees of the graph, but I want you to do it of these betweenness and closeness centrality values. All right. From this part where you got until at least two components, I want you to do the breadth first and depth first search forest, like we did with the original graph. We only had one breadth first search tree that we considered, but since we have at least two components, we'll have multiple trees, which is a forest by definition. And so I want you to be able to plot that graph. So I want you to have a figure like the one we had in class last time. Okay. So this will be posted sometime within the next few days, and then it'll be due. I'm thinking of making the assignments 1 week after assignment 4. So each assignment will be a week until assignment 7, whenever that is. Okay. So any questions about that? So I'll go over all this today. So don't worry if you don't understand some of the terminology here. All right, and so the main thing you're probably thinking about now is the midterm. So the midterm will open this at midnight tonight, I think. Yeah, 8 hours. So I want you to sign up for this, and then it'll be due about a week later. It says on here when it's due, but it's about a week. And so what you'll be doing here is you'll be given a whole bunch of exercises to do, and then develop Python code for each of the exercises here. And then basically you'll be trying to pass test cases that are on HackerRank server. Okay, so I'll show you what just some of them here. So they're arranged into 3 categories. So each of the more easy problems, in my opinion, are worth 5 points. Then the slightly more difficult ones are the 10-point ones, and then finally the last ones are 15. Okay.
Do you want us to do all of them? Is there like a number you want us to do?
I would like for you to do all of them, but each problem has partial credit. So the number of test cases you pass for a particular problem times the point value is what you get for each one. And there are 200 points available here, and if you get 100, you basically got 100 on the midterm. So once you get to 100, you're done.
Same as HackerRank, like we submitted
Yeah.
as many times as you can.
Yeah. Yep. So here's just an example. So I'm not going to actually solve it. So the way that it's given is it's given a description of the problem, like maybe some motivation and stuff like that. It tells you what the input format is, and then maybe constraints, then sample input output. And so maybe I'll just, it gives me an input string S. I'll zoom in. So let's just say that since it gives me a string, it'll be through input. So it's not through this sys.argv thing, it's through input here. So let's just say S is that particular string. Maybe I just want to print S. This doesn't solve the problem, but I'm just showing you as a demo. So we can run the code just against a few of the sample test cases, and it'll tell me, oh, you didn't pass the test case, and this is what you got. This is what it's expected to get, and this is what you actually printed. And same for here. But then let's just say that I actually did the problem and I think it's correct because I passed these 2 test cases. Then I can click submit code, and I say yes. And you have unlimited submissions here, so don't worry about that. And it'll say, no, you didn't pass this, any of those. So you got to score 0 here. But if I pass, say, all I guess all 9 test cases, then I would get 5 points on that problem. If I passed, if I passed, say, 5 of them, I would get 5/9 times 5, whatever that is. Okay, and then that's basically all of the problems here. And then you'll be, I guess there's a rank here, and then it'll also tell you on the leaderboard once more people sign up what your score is. So unfortunately, I'm going to be capping the amount of points you get. So once you hit 100 or go over 100, there's no point in getting more points. So once you hit 100, you're pretty much done. Okay? So any questions about the midterm? So it'll open midnight tonight, and it'll be due about a week later. Okay. Yeah, so there are 200 points available. 100 points is the max you can get. Yeah, once you hit 100, you're done. Yeah. You can do more if you want, but in terms of credit, you won't get any more. Yeah. Any questions before we get back to the material? All right. So we've been talking about these graph things, right? We've been talking about many different properties of graphs, like complete graphs, cycles, paths, a whole bunch of things. And then one of the main questions we wanted to understand was, how do we explore a graph, right? How do I figure out what this graph structure is like? And the one thing that we talked about in terms of what the structure could be is try to start at a particular point in the graph and then just explore the graph, right? Explore what vertices I can reach to in a certain number of edge traversals. And so the 2 algorithms that'll let us do that are breadth first search and depth first search. So breadth first search works by choosing a particular vertex, then exploring everything I can reach in one edge traversal, then everything I can go into in two edge traversals, everything in 3, everything in 4, until I explore the graph all the way through, right? And so the idea here was that we maintain a queue of what is called the frontier, of all the vertices that are on the outskirts of what I'm looking at. And then if I see another vertex one step out, and by that I mean that its color is white, so I haven't seen it yet, then I add that to the queue of basically where the frontier is. All right, and then I just explore the graph that way. And then I assign distances along the way. So the starting vertex, which I denote S, will be 0, since the distance from S to itself is 0. Then everything I can reach in one edge traversal is distance 1 from S. Then everything outward from that is distance 2. Everything out from that is distance 3. Pretty simple. And then we figured out that the runtime of this algorithm is linear in the size of the graph. We may explore every vertex and every edge. Then we figured out another way that we can explore the graph, which is start somewhere in the graph and then just go in one direction until I can't go anymore. And then once I reach a point where I can't explore any vertex at all, I backtrack to the last point and then retry, right? So that was depth first search. And the idea here is I assign these 2 values for every vertex to help me figure out what I've explored at what time. So I assign, what did I call it? A discover time and a finish time for every vertex. So I started at this particular vertex, and then I explored one vertex that is a neighbor of what I'm currently looking at. It doesn't matter which one I pick as long as I pick one. And then I explore until I can't reach anymore, because this vertex can't go anywhere else to another white vertex. And then therefore I color it black, so I'm done with this going this direction, so I backtrack to the last point. To the last point, which is the left vertex, and then it sees this other vertex, which was a white neighbor, so I explore that way. But this one can't go anywhere, so I mark it black, backtrack, but I can't go anywhere else, backtrack, and then I just explore the graph in this way. But I get to this point and I say, well, the starting vertex was black, so I can't explore anymore, right? So what do? I pick another vertex, which is white, that I've not seen. It doesn't matter which one I pick as long as I pick one. So the one I pick is this top right vertex, and this is my new start of the tree that I'm going to build. So because it didn't exist in the tree that in the original source vertex, so I'm basically making another tree here. And then I explore with this one. And then at this point I say I've explored every single vertex, so I can't explore anymore, so I'm done. So we note that since we had to restart our computation, we basically made another tree. So we have one tree which is composed of these 6 vertices on the left, and another one which is these 2 on the right. So basically we're computing a forest, a bunch of trees. But the idea here is that we explore the graph in a different way. We explore in one direction until we can't anymore, then we backtrack. Okay? Any questions about what we've gone through so far? All right. So we covered this. So now we're going to cover, which is probably one of the most famous algorithms in computer science, which is called Dijkstras Algorithm. Anyone know of Edgar Dijkstra, which was the pioneer of this algorithm? What?
Oh, you mentioned the name last week.
Yeah. So that was the guy who published the paper which contained this algorithm, which is basically it does single source, shortest path. So like with breadth first search and depth first search, we started with one vertex and then figured out the distances to everywhere else. So you're thinking, why not just run breadth first search, right? Because it's linear in the size of the graph. You can't do better than linear time, right? Because you have to read the entire graph anyway. And Dijkstra's algorithm has actually a worse asymptotic running time. So why should I use this, do you think? It takes account of weights. So breadth first search marks the distance of vertices as the number of edges traversed, right? Wouldn't that not make any sense with, say, Google Maps, right? Some freeways go a lot further than some other roads. It wouldn't make sense for each possible road to have the exact same distance. So we should be able to account weights into here. But breadth first search and depth first search do not take that into account. So what Dijkstra's algorithm does is it does shortest paths and takes account into weights. Okay? And so at the end, it'll assign to each vertex a distance from the source vertex, which is the shortest distance along those edges, accounting for the weights on the edges. But we note that breadth first search is equal to Dijkstra. It's the exact same thing if all edge weights are 1, right? Because if the edge weights are 1, that's just counting edges anyway. So if we have anything else other than edge weights to be 1, then we can't use breadth first search. So we have to use Dijkstra's algorithm here. It's actually a simple exercise, but I won't show it here, that you must have positive edge weights. Because if you have negative edge weights, it doesn't necessarily work. So in the next section, we'll actually cover an algorithm which has a slightly worse asymptotic running time than this, but it accounts for negative edge weights too. All right, but we're not going to get there yet. So how do you account for edge weights? So we have this way of thinking for breadth first search, for example. If we are at a vertex and we're looking at some other vertex that has some distance and we've seen it already, so we know our distance and we know the distance to the one I'm looking at, right? And we know its shortest distance so far. So what do you think is a good idea? Let's just say that the one I'm looking at, like the way to me, along this other edge I'm looking at, is shorter than the distance to the one I'm looking at.
Last time your traffic
Yeah,
Paragraph of whichever one's-
right, just take the minimum of the two, right? So that's basically what we're going to do. So we're going to maintain this value for each vertex as the shortest distance so far for each one. And if we find some way to get to the vertex we're looking at with shorter distance, then we just found a way to get there with shorter distance, so we must update it. Okay? That's the basic idea. So what we're going to do is we're going to take in a graph G and a source vertex S. As we all know, the distance from S to itself is 0, and we set the distance to be infinity for all of the vertices. The same as breadth first search. But we're going to maintain this distance to be the minimum as we go along. So what we're going to do is we're going to let S be the set of visited vertices. So it's a little bit different than breadth first search in the sense that we're going to, instead of maintaining the frontier, I'm going to maintain the set of vertices I've seen at all. Okay? Because if I maintain the frontier only, then I'm going to only be exploring the frontier vertices again. I'm not going to be exploring the other ones. So that's why I have to keep the set of all visited vertices so far. Actually, that should have S in there, I think. But yeah, I think that should have S in there. All right, so Q is basically, we're going to be exploring the graph by popping off a vertex every single time. So what we're going to do is we're going to look at the vertex that is currently in Q and pop off the minimum element in there. Okay, so it has the minimum distance value to all other vertices. So when I start this algorithm up, which vertex is that? What, the first iteration? S, right, because every other one is infinities, and this is the only one with 0, so it would be S the first time. So let's think in terms of S. What do I want to do? I want to explore all of my neighbors, right? So I'm going to add this vertex U to S, which is the set of visited vertices. So it didn't need S at the beginning. I was wrong. So I'm going to look at through every single neighbor of U to be V. And so we want to check if the distance to this vertex is, if the current value assigned to this vertex V is larger than through this other path, through the one I'm currently at, and the edge to that one, then I just found a shorter way to get there, right? So therefore, I must update it, right? Does that make sense? Don't nod if you don't understand, right? So yeah, this is the critical part here. It's saying that if it has a set distance and I found a shorter way to get there, then I must update the shortest distance there because I just found a way to get there, right? So I'm assuming that you can compute the weight of two vertices, the edge between two vertices in constant time, but that's a minor point. Then if it's greater, then I set it to be equal to this distance so far, right? You can actually modify this to say the current parent pointer of the newly set vertex is the one I currently am at, right? So by doing that, you can reconstruct all of these paths, but I'm not doing that here. I'm just doing the distance itself. All right, so if the distance is greater than, then I update it. And then I return the distance values, right? It's just basically breadth first search, but just a slight modification for maintaining this distance value for every vertex. All right? So any questions on how Dijkstra's algorithm works? It's actually quite amazing that it's just a slight modification of breadth first and depth first search. It's just you have to maintain this distance and keep the minimum for each of the vertices. But that's the only thing you need to change here, basically, right? It really isn't that much of a change.
So basically just make sure you have the minimum distance for each one, and then like if you find a lower one, then just update it.
Right, yeah, it really is that simple. All right, so let's just try to analyze the runtime here. So we know that the number of edges, so vertical bars around a set, means the number of elements in it. So here I'm saying that the number of edges is big O of the number of vertices squared. So why is that true? Let's
look at every vertex twice.
it's squared though. So V times V. So let's think, well, I say here for any graph. So let's think of a graph, say n vertices, with the most number of edges possible. So the complete graph, right? So there's an edge between every single pair of vertices. So how many edges order is there? So every vertex has n minus 1 edges to all the other n minus 1 vertices. N times n minus 1, it's order n squared, right? So therefore, that's why I have this here. So the number of edges is order of the number of vertices squared. It could be less, but I'm saying that it can't be more than this. This is the absolute most it could be. Okay? So we can find the minimum of some set or list Q, finding the minimum in that set in the number of vertices time, right? The first time I just search through the list of vertices until I find one that has the smallest distance, right? Because you can find the minimum in linear time. So we can certainly do this in linear time. Could we do better? Find the minimum? Actually, there are two ways you can do it.
Yes.
No, there's actually just one way, yeah.
You can you do like a binary sort.
So I can do sorting and then find the first one, right? But the problem is that I may update the largest distance vertex to be, which will be even smaller than the smallest one. That could be possible, or at least it could be really small. So it might not necessarily work here, but you can do better. Min heap. How many of you do not know what a heap is? Yeah, so a heap is just basically a data structure which allows you to have, let's just say min heap. So it has the minimum element for the top. It's just a binary tree in a sense, but the minimum element at the top, and each of the elements, the left and right child, are less than or equal, or in this case, greater than or equal to that top element. And then you keep going. And so if you want to add an element to a heap, you add it to the very bottom of the tree and then move it up as necessary. And then just extracting the root. So when I'm doing this algorithm here, when I say min of Q, I'm actually removing it from Q. Because I want to extract it from Q and then after that get the minimum element again. So for a heap, I need to remove the minimum element. So I extract the root. Does anyone know what we do then? In order to re-heapify the tree. Well, there's nothing at the root now.
Place the minimum at the root.
Well, it actually doesn't matter what I place there. So what I can do is I can just take the last element in the tree and move it up. Yeah, because it doesn't mess up its parent, but it could mess up like the relationship at the top. So then I move it down as necessary, right? So since I'm adding an element at the beginning of the heap, not the beginning, the end of the heap. So this is a complete binary tree, right? So what's the depth of a complete binary tree? How many levels could it possibly have for n elements? Log n, right? So therefore, I can extract the minimum of a heap in logarithmic time. So by using a min heap, I can reduce this to log of the number of vertices time. Okay? So just by using a different data structure that you've seen before, like what's a heap useful for? It's useful here, right? In maintaining what's the minimum element over time. All right? So let's see. So let's look at this. So Q is the number of vertices, right? And so this will be linear time, number of vertices time. And so therefore, extracting this minimum is logarithmic the number of vertices time. So we know it's at least, the number of vertices times log of the number of vertices. But the problem here is that we may, we're going to be exploring all of the edges of the graph too. So not only are we going to be exploring all the vertices, but also all the edges. But for each one of those, we're going to be extracting the minimum element. So therefore, the running time of this algorithm is number of vertices plus the number of edges times the log of the number of vertices. What was breadth first search's running time? It was actually the number of edges plus the number of vertices, because in breadth first search what we did was we explored the edges and all the vertices of the graph. And we figured out that for each edge, we're going to only see it twice, right? Because it only corresponds to 2 vertices, and we only see each vertex one time, right? So we're going to only traverse that edge twice. So breadth first search, therefore, is 2 times the number of edges plus the number of vertices. But in big O notation, we take out all constants, so it's just the number of edges plus the number of vertices. So the only thing we really lost here was an extra logarithm here, right? But what's the power that we gained? What we gained was we're able to account for edge weights, right? We gained all that power for only a logarithmic cost. And the algorithm doesn't change very much. So that's one of the main reasons why this algorithm was so successful and so widely known. Okay? So I know it's past the project deadline, but you can use what is called the Fibonacci heap. So it relates to the Fibonacci sequence, and you can reduce the runtime even more. But the point here is that even changing the algorithm a little bit to get so much more capability from it, you only take a little bit of a hit in runtime. Okay? So any questions on Dijkstra's algorithm? I think that's it, yeah. Yeah.
Quick question just about heaps.
Uh-huh.
So, the way you explained it, it sounds pretty much like a binary tree.
It is. It's a complete binary tree. Yeah, but it's not a binary search tree. There's a difference. So binary search tree is for let's just say the root. The root has smaller elements on the left-hand side and greater elements on the right-hand side. So like it kind of splits the set of elements, right? For in this case, for a heap, let's just say it's a min heap. So the minimum elements at the top, and so everything is greater than or equal to it on either side. I don't know what it is on otherwise in the heap, but all I know is that the minimum's at the top, right? So what I'm going to do is I'm going to extract that minimum element, if I want to remove it, then take the last element in the binary in this tree, which is going to be on that last row, and I'm going to move it up to the top, right? It may work with the with having both of its children being greater than or equal to it. I don't know that, but let's just say if it did, then we're already done, right? But because we didn't mess with any of the rest of the tree.
Oh, and then you bring it down
Yeah.
as it needs.
Yeah, I swap it with its child until it's at the right place, and therefore I'm already set.
Gotcha.
So any questions about Dijkstras algorithm? All right, so before we wrap this section up, let's talk about what we've talked about with respect to search algorithms. So what we were able to do is there's a main theme between these 3 algorithms. The idea was we start somewhere and then we try to explore the graph in some way. So breadth first search says explore everything that I can within my neighborhood. So I haven't used that terminology, but neighborhood means all of my vertices that are one step out from me. So I explore, yeah.
So your neighbors.
Yeah, exactly. So I explore everything within one edge, then everything with 2 edges, until I explore the whole graph. For depth first search is to explore in one direction, then come back, then explore another direction, then come back, etc. And then backtrack as necessary. for Dijkstra is basically the same thing as breadth first search, but now we have this weighting on the edges. But all of them have this property that we're exploring the graph in some way from some start vertex, right? Yeah, so this is what I just said. And then we update the minimum value for Dijkstra. But the point here is that all of these algorithms have the same philosophy behind them, right? You start somewhere and you explore the graph in some way. All right. Any questions on all of these search algorithms? All right. So that was one big thing that we wanted to look at, right? We wanted to look at the structure of graphs in some way. So what's another way do you think we can look at structure of graphs? Maybe we want to, say, assign some importance metric on each of the vertices. Like, these set of vertices are important, these ones are not important, right? In some way, right? So what are some ways that we may deem a vertex to be important to the structure of the graph?
How many edges are going from it?
Yeah, so the number of edges go into it. What's another one?
Whether it's connected or how many things it's connected to.
Yeah, so the degree of a vertex, yeah. What's another one? What if, like, say, if we're modeling a graph in terms of, like, the router network of, say, ASU, and then one router goes down, and then it splits the network into two pieces. That'd be kind of an important vertex, right? So we can think of that as maybe a vertex that is considered a bridge vertex in a sense, right? It's bridging some set of vertices with another set of vertices. And if I take out that vertex, then the graph becomes disconnected. We may think of it that way. What's another one? Maybe in terms of like Dijkstra, with when we have edge weights, we may want to find the vertex that is closest to all of the other vertices, right? Maybe that's an important metric. So all of these are what are called centrality metrics, right? And these are extensively studied in the literature, but the main idea is that they're all centrality metrics in some sense. So the example with the how many neighbors a vertex has, that's called degree centrality. The closest vertex to all of the other vertices, in some sense, that's called closeness centrality. And then the one with, which is the bridge between these sets of vertices, that's called betweenness centrality. And we're going to go over the last two. So distances may be useful in some sense, but it doesn't tell us anything about the structure of the graph in terms of how vertices are related to each other. So how do we look at that? We can look at degree distribution, how vertices may be important in some way. So what we try to do in centrality is try to assign a value to each of the vertices, right? So in terms of, say, a higher value means more important with respect to some metric. And then some of the metrics are the degree of a vertex, shortest average path. So that's what I meant by closest, the shortest average path to all of the vertices. More shortest paths passing through it. So maybe I want to give a score to this bridge vertex for betweenness centrality, but maybe I want to find the betweenness of other vertices, which may not necessarily be a bridge. Like maybe if I delete them, maybe it still stays connected, but it may be important in this metric still. So the way that we're going to do with that is we're going to assign betweenness to be the number of shortest paths which pass through a vertex. I'll go over that when we get to it. Another one that I'm not going to go over is, I think it's called density. So what this is you look at all your neighbors, and you want to figure out how much of a clique that is. So what was a clique again?
Vertices that are all connected.
Yeah, so it's basically a complete subgraph, a subgraph that has every single edge between all of the vertices in it. So you may want to figure out how densely connected you are to all your neighbors, right? So that may be another metric, but the whole point here is that you're going to assign some value to each vertex with respect to some metric. All right. The slides are not going. All right. Slides weren't going. All right, so some applications of centrality. The biggest one is social networks. So when I talked about betweenness, it's these number of shortest paths which pass through the vertex. So in terms of a social network, that could possibly mean that that's how the information travels, right? If most of the information that flows through a network passes through you, then you're important with respect to that social network in that way. All right, so that's one application. Social networks finding which topics are being discussed the most. So that could mean like, in the sense that you're a vertex and you have an edge to a topic if you're discussing about it. So you can say, look at the topics and say, which of the topics has the highest degree at a given time, right? Because those are the ones that have the highest are being discussed the most. Networking. Yeah, essentially, yeah. The one example I gave earlier about routers failing and working was finding which router has the most number of packets in a given amount of time. So that could be either degree or betweenness centrality, depending on how you look at it. Wikipedia, one of the project ideas was to explore the graph of Wikipedia and figure out what topics are being discussed the most. So you can see a theme here, like it's about how information travels through a network. So that's one of the main applications of centrality with respect to graphs. All these are important for analyzing a graph in terms of the structure. So we're really now getting into the part where we're talking about the actual structure of the graph. All right. So we're going to be talking about closeness centrality and betweenness. So closeness, I'm going to go into detail, but I'm going to not go into all that much detail about betweenness because it's a little complicated, and you could read the original paper if you want. But so closeness centrality means the smallest average path, average length path to every other vertex. So this is basically finding the vertex that is closest to every other vertex. Yeah, so I'm going to go over this and then we'll take a break. So it's a measure of how close a vertex is to all other vertices. So I'm going to assign a vertex I to have a value of closeness of I to be the sum of the inverse of the distance to all the other vertices. So Dij means the shortest distance from vertex I to vertex j. So let's think about that. So let's say that we're looking at a vertex which has the highest, it has the smallest average distance to everywhere else. So it really is the closest one. So if we add up all of the Dij's, so of all the distances, then it's the smallest, right? Because it's the closest to every other vertex. So a small number, what is 1 divided by a small number? A big number, right? So now let's look at a vertex that is far away from everywhere else, right? On their average path. So if you add up all the Dij's for that vertex, then it's going to have a really large value. So 1 over a really large value is a small value, right? So this really does capture what closeness really means here. And so what we're going to do is run through every single pair of vertices and then find the distance corresponding to those two vertices, and then at the end sum them all up and then do 1 divided by that number for each vertex. So these algorithms are in network X, so you don't have to implement this yourself. So what you're going to do here is you're going to loop through every vertex, and in this for loop, I'm going to determine the closeness value of S. So what we're going to do is we're going to maintain a queue of the frontier of vertices, just as before, for breadth first search. The distance is currently infinity for all vertices. And it's almost exactly the same thing as breadth first search. But the main difference here is that we're going to actually maintain, actually it is pretty much the same thing as breadth first search. Yeah. But at the end, what we're going to do is, so far of S is going to be the sum of the shortest distances everywhere else. And then I'm going to assign the closeness centrality of S to be 1 over this sum, right? Just as we talked about. And then just what the main algorithmic part is basically doing breadth first search, but the condition here is testing if the distance is infinity. That's basically if the vertex is white. Yeah, it's the same thing as breadth first search. But I'd welcome you to look at the details of this, but that's basically how the algorithm works. It's just breadth first search again. So any questions about this before we take a break? All right, let's take a break. We just covered closeness centrality. So the main idea behind closeness was to find the total distances to all the other vertices, and then find the vertex which had the minimum one, right? And in a sense, the minimum here is finding these distances for every vertex, and then do the inverse of it. So the vertex which is the closest to everywhere else will have 1 divided by the smallest number, which will be a larger number. And the vertex with which is the farthest from everywhere else will have 1 over a very large number, which will be a much smaller number than the other one. So the idea here was we maintained in far of S to be the distance, the total distance from S to everywhere else. So the idea here was that it's basically breadth first search all over again. And then once we found the sum of all distances, we did the inverse of it. And so the idea here was that it's almost exactly the same thing as breadth first search, but instead of maintaining color for every vertex, what we do is we determined what a vertex means that we've never seen it before, which means that their distance is infinity. All right, so any questions on how closeness works? All right. So just as an application, so this is from my thesis, my undergrad thesis, which, so what I wanted to do was, I have one graph corresponding to each of the years in terms of sea ice concentrations. And so what I wanted to figure out was, what is the vertex which has the highest closeness value, right? Is some vertex in the graph, what are some properties of that? And what I was able to find was that if you look at, so I plot the x and y coordinate, and don't worry about what x and y really means here, but the thing is that x and y correspond to position, like the physical position on the in the Arctic Ocean. So here you can see that the x position, other than a few random cases, is roughly the same position. And also the same thing for the y position. So what I was able to conclude from here is that the vertex which is the closest to everywhere else was located physically near each other. Most of the time it's in one particular area. So this is just yet another application of centrality, in this case closeness. And in my thesis, I don't have it here, but I also looked at betweenness, centrality, and things like that. All right, so let's look at the runtime. So it's doing a breadth first search on the graph, but the thing here is that instead of doing it from just one vertex, we're going to do it from every vertex. Just start from one vertex, do breadth first search, start on the next one, do breadth first search, all the way through the graph. And then find the closest centrality value of each vertex at each moment, at each time. So breadth first search takes linear time in the size of the graph, and we have order v vertices to choose from because we're just going to do it from every vertex. And so therefore, if we just do v times v plus e, it's just v squared plus v times e, right? It's just simple multiplication. Any questions on that? Okay. So the last thing we're going to go over in these slides is betweenness centrality. So we want to look at vertices which connect two communities in a sense, or two components together. So it's actually not called a bridge. An edge is called a bridge, which means that if you delete that edge, then you basically increase the number of components in the graph. In a sense, if you delete that edge, then you disconnect the graph, right? And so in this case, it's a bridge vertex. So we want to find what is the most bridge-like a vertex is. So if a vertex is a bridge, then it should have a really high betweenness value. But if it's kind of bridge-like, but almost not really, then it should also have a high value, but maybe not as high. Okay? So we give a higher score, a betweenness score, for how bridge-like a vertex is. So I'm going to go over what bridge-like means. So we want, because if you think of what a bridge vertex is, most of the information between these two camps goes through that vertex, right? So if we look at all of the paths that could possibly appear in this graph, most of them are from this camp to this other camp, or from this one to this one. So in a sense, most paths pass through that vertex, right? So we may want to think of this as the number of shortest paths that pass through you, okay? The higher percentage of all shortest paths that exist that pass through you, the higher your score. So what we do is, well, we don't really do this, but we want to count the number of shortest paths that possibly exist in the graph, right? And we want to, for each vertex, find the number that passed through it. And then keep the percentage of the ones that pass through it as the score for betweenness. Okay? So that's the high level goal here. So just for formality reasons, I'm going to let that symbol is sigma. So sigma of ST corresponds to the number of shortest paths which go from S to T. And the one with parentheses with the vertex in between means the number of those which pass through V. Okay? So the first one means just the number that exist at all, and the second one means the number of ones that pass through a vertex, a given vertex V. And of course, V has to be different from S and T, right? Because if it were equal, then it would be trivial in definition. So what I want to calculate here is basically for all other vertices, we define the betweenness centrality of a vertex V to be all the other vertice pairs, so S and T. I'm going to loop through all the vertices S and T other than V, and I'm going to find the number of ST paths that pass through V divided by the number of ones that exist at all, and I'm going to add them all up. Right, because if I choose two of them wrong, like S and T are bad choices, then this quantity will be really small, right? But it may be the case that V is a really high quantity that has a high betweenness value. So I need to loop through every pair of S and T, right? And then I just calculate all these percentages, add them all up, and that's my betweenness value for this vertex. Okay. All right. If a large number of these pass through V, then it has a high betweenness value. So the algorithm that's on the next set of slides is from Brandis, which came out, I guess, 15 years ago. Well, let's think how we would do this, right? So I got to calculate this betweenness value for all vertices, right? So which is order V. So how many pairs of vertices do I have to look through for S and T? Well, there are order V vertices for each one, so V squared pairs I have to look through order V squared. So therefore, I'm already at V cubed running time. But now I gotta find the number of shortest paths, and we don't even know how to do that. That could be really inefficient. So this algorithm is actually quite simple, in a sense, in terms of its runtime and how it was created. So what you do there is, this algorithm finds the betweenness value of one vertex. So we can just run this algorithm V times for all vertices in the graph, and therefore I have a V squared times E running time. For network X, it's just a simple method call, and X dot between the centrality of G. And it returns to, I think it returns to a dict, which corresponds to vertex betweenness value. Key is vertex, value is the betweenness centrality value. So the algorithm, I'm not going to go over it, but there are a few more things you have to keep track of, and I won't go over them because there are some lemmas that you need to prove in order to justify why these are, why you need to have these. But the essential thing is that you're going to be exploring the graph kind of like breadth research, but not exactly the same way. Okay? So, but the point here is that this is our high-level goal, right? I want to calculate the number of shortest paths which pass through each of the vertices. Divide by how many that possibly exist. All right? Any other questions about centrality, graphs, any of this material? So in assignment 5, what you'll be doing is you'll be finding closeness and between the centrality values and then doing a plot of that. So like you'll see what does the between the centrality value look like over time. So are there some vertices which have really high betweenness value, or are they all pretty much the same, right? So that's what you'll be doing in your assignment. All right. So I'm not gonna do very much of this next section, but so I'll let you go a little early, but let's just do one little bit of dynamic programming. So how many of you have heard of dynamic programming? All right, so only a few. So why do we need another technique?
Isn't technically this is better than that static?
Right, so,
Update it as you go.
yeah.
Dynamic sounds edgy.
I'll actually go over where this term came from, which is amazing. It's actually really, really fascinating where it came from. Recursive algorithms are too slow, right? So one example of an algorithm that we've seen that's really slow is Towers of Hanoi, right? Moving all these pegs to another, all these disks, I get this wrong every time. Move all these disks on one peg to another peg, right? And so what we did was we found that the recurrence of that is T of n is equal to T of n minus 1 plus T of n minus 2, right? And we, if you actually work through the details, that's an exponential running time, right? Which is insane, right? These algorithms are really slow. Like another one is Fibonacci numbers, right? What we have is we call fib of n minus 1 plus fib of n minus 2. So that's an exponential time algorithm, right? But it turns out you only need to maintain 2 values and then just add them over time. And it turns out you can get a linear time algorithm for Fibonacci numbers instead of an exponential time. So recursion, we can't just do recursion, right? So what do you think is the main idea behind dynamic programming?
Creating code with other code.
In a sense. We'll think about the Fibonacci call. So we call fib of n minus 1 and fib of n minus 2. What does fib of n minus 1 call recursively? Yeah, so I call fib of n minus 1, fib of n minus 2. Fib of n minus 1 is going to make 2 recursive calls, right? What are those recursive calls? But I just did it over here, right? So I'm recursively calling it twice. Did I need to do that? No. So I'm doing an extra recursive call that I didn't need in the first place. So what do you think I can do to remedy this? Exactly. That's the essential idea behind dynamic programming. Even with divide and conquer, it was slow. So some algorithms are slow even in practice. Can we do better? Don't store all of the previously computed values and access them later, right? I don't need to compute things that have already computed, right? That's stupid, right? So what you want to do here is you want to store it in some way and then access it in some way at a later time. So I don't have to recompute things. So we can store things in a table, in a list, a dictionary, all sorts of things you can do here. But the main idea here is you store previous computation. Okay, so any questions on what our high-level goal is here? So we're going to basically be going over 7 or 8, I forget the number, algorithms which involve dynamic programming. So this idea of storing previous computation and then resuming it by basically accessing the table in some way. So where did this dynamic programming term come from? So it's actually from, does anyone know who Richard Bellman is? So we're going to go over an algorithm which is called Bellman-Ford. So Bellman worked for the Rand Corporation, as you'll see in a second. Famous computer scientist, all sorts of things like that. So this came from his autobiography, right? And so he is the one who actually came up with this term, dynamic programming. Okay? So I'm just going to read it. An interesting question is, where did the name dynamic programming come from? The 1950s were not good years for mathematical research. It's actually not from Bellman, but he popularized it. We had a gentleman in Washington named Wilson. He actually had a pathological fear and hatred of the word research. He would turn red and he would get violent if people used the term research in his presence. The Rand Corporation was employed by the Air Force, and the Air Force had Wilson as its boss. I had to do something to shield Wilson and the Air Force from the fact that I was really doing mathematics. I was interested in planning and decision-making and thinking. I decided, therefore, to use the word programming. I wanted to get across the idea that this was dynamic. It's impossible to use the word dynamic in the pejorative sense. Thus, I thought dynamic programming was a good name. It was something not even a congressman could object to. Isn't that amazing? There's more detail hidden here through the ellipses, but I encourage you to read Bellman's autobiography. All right. Yeah. So I thought that was just amazing. So the main ideas behind dynamic programming, I just outline a few steps. So the idea is we're going to be doing recursion, but we're going to do smart recursion. And why is it smart? We store the previous computation. But the first thing you got to do is define the subproblems, right? Just like in recursion. So we want to count the number of subproblems, which will help us get the runtime in a second. Then we're going to guess, which means that we're going to guess that these recursive calls do the correct thing. Then we count the number of choices that could possibly happen. We relate the solutions of the subproblems together in some way, and then find the time that it takes per subproblem. Then we do recursion with memoization. So what does memoization mean? It is memoization, but it's basically just a fancy word for store previous computation. So what usually people say is we store things in the memo, right? So that usually means a list, dict, but it's just another term that people use. So the time that it takes to run a particular algorithm is the number of the time per subproblem times the number of subproblems. Right? That's essentially what we need to do here. And then using these subproblems, we're going to solve the original problem in some way. Like for Fibonacci, we call n-1 and n-2, and then how do we solve the nth case? We just add them together, right? So we're going to get to more complicated examples, but that's the essential thing. So it's the total time of the algorithm is all the recursion time plus the time that we need to combine the solutions, right? So for for Fibonacci numbers, it's whatever time it takes to compute the recursive solutions, and then doing addition takes linear time in the size of the input, or constant time if you want to think of it that way. All right. So the first example that we're going to do, and then we'll quit for today, is Fibonacci numbers. So it's the numbers that you all know. So the first one's defined as 1, and the second one is 2. Some people define it as 1 and 1, but it doesn't really matter here. And then recursively, it's the n-1th number plus the n-2th number. And then this is recurrence relation. So this is just the recurrence that we've seen before, like for Towers of Hanoi. So what's the solution? It's this complicated number, which if you do it exactly, but if you want to upper bound it easily, it's 2 to the n running time. So it's exponential. This is actually exponential running time, but it's slightly less than 2 to the n. But the whole point here is that it's exponential running time. The thing here is that this value is the nth Fibonacci number. So it's equal to some number to the n minus some number to the n over the difference of the two values. So why can't we compute that number directly? So we can just compute the nth power of each of them and then just do 2 subtractions and we're done, and a divide. Why can't we do that? So what does the number look like here? Is it a nice number? No, it has radicals, right? Can we store radicals on a computer? No, right? Because it requires infinite precision for non-square numbers. So we can't compute it directly, although this is the correct number. So the idea here is let's just implement a naive algorithm, then we implement a smarter algorithm. So let's just do a naive one. So the Fibonacci number of n, the nth Fibonacci number is, well, if it's 1 or 2, then we just return 1, right? The first number or the second number is 1, so we just return 1. Otherwise, what do? We call fib of n minus 1 plus fib of n minus 2. Simple, we've seen this before, okay? We've seen that before, so let's just look at the runtime. It's the solution to the recurrence we already saw, right? But in this case, it's the running time of the algorithm versus the actual number itself. And then constant time to combine the solutions, but it's negligible. So what can be said about f of n and n plus 1? So this is just a technique to upper bound the recurrence. So we can say that the n minus 1th Fibonacci number must be larger than the n minus 2th Fibonacci number, clearly, right? So therefore, we can actually put an upper bound here. So t of n minus 1 plus t of n minus 2 is at is at least 2 of t of n minus 2, right? So if we actually go through the recursion, the steps to evaluate this recurrence, well, we have 2 copies of an n minus 2 subproblem. So every time we decrease n by 2, we double the amount of running time. So it's order n times, I'm multiplying by 2. So therefore, we have an exponential running time here, which is wrong, right? Because what did we come to the conclusion? We came to the conclusion that we're computing subproblems we've already computed, or we're going to compute many times, right? So what we want to do is we want to make sure that once we compute a value, we store it and never compute it again, or at least never do recursive calls with that. Not sure what. Yeah. So if we expand the recursion, we have 2 copies of n minus 2. Then we'll possibly have more of n minus 3. N minus 4 is going to have more recurrence calls. So there's no need to do that. So what we want to do is we want to memoize everything in some way. So we can usually use a table or a dictionary, whatever you want. At a given point, what we want to do is we want to look up the value. If it already exists in the memo table, then I just extract the value and return it directly, right? Then I never really computed anything. But if it's not, then I do a computation of it because it's not in the table. And then once I do the computation, the important part is I stick it in the table, right? So if the value is not there, then we do the computation and then store the value in the table. So I didn't fix this, but when we're given a particular number n, I want to calculate f of n, the nth Fibonacci number. So what's a good data structure to use here? So I have a value n and f of n that I want to store. So, well, I want to relate n and f of n in some way.
Binary tree or
I don't think you need it to be that complicated. what's an easy way to relate two values together?
Oh,
Dictionary, right? So a dictionary can do this easily. So you can let the key be n and the value be f of n, right? So the key n maps to f of n, right? So a dictionary is an easy way, although there are other ways you can do this. So as I mentioned earlier, you can actually use two arrays, and then for each, the nth index, no, you can actually just do one array. You can have an array which has n elements in it, and the ith element is f of I, right? So the index will be the key in a sense, yeah. It's essentially the same thing, but it's even simpler than a dictionary. But Python has dictionaries, and that's what makes it easy. So what we're going to do is we're going to store a dictionary. I'm going to call it memodict. So now when I call fib of n, if it's in the table in this dictionary, then I just return the value corresponding to n in the dictionary, right? If it's in there, then I don't need to compute it again. Then if it's 1 or 2, then I return 1. Actually, I should also store in the table here, right? Although you can make those two default values, but anyway, you actually don't have to because it's only a few times are you going to hit 1 here. But otherwise, what we're going to do is we're going to calculate the value first. We're going to capture the value, store it, then return it, right? Because if I just say return fib of n minus 1 plus fib of n minus 2, then I just threw away the value, and I didn't store it in the table for later, right? So what I want to do is I want to capture the value first, store the value as the value corresponding to n, and then I return the value, right? So that's essentially the algorithm, right? Yeah.
This doesn't necessarily relate to
Yeah.
it, but if you, could you technically split fib n minus 1 and n minus 2 up into different threads? And would it run faster that way?
You would have an exponential number of threads then. It would be
I see.
because you're going to still be doing the computation of the fib n minus 2 twice. So
that wouldn't make sense at all, yeah.
right. So what you want to do is you want to avoid doing computation you've already done. Yeah. Could you? I'm trying to think how you would do this in multiple threads. I'm not sure, but because there's a nice linear time algorithm to do this, which I'll show in a second. But any questions on why this works? So the idea is capture the value of recursive calls, store it, then return it. All right. So we only do recursion if n is not in the table, right? And only once when it happens, because if we're at some other point and we want to do recursion on n, well, I check if it's in the table first, right? Because since I've already stored it, I only do this recursion one time. What are the possible calls? Well, the ones that won't be in the table are fib of n to start with, n minus 1, n minus 2, all the way down. We only make n recursive calls because we know that none of these will be called twice, right? Because of that previous bullet point. So what's the time per recursive call? Well, it's storing in a table, looking up in a table, comparing values. I just say that's constant time, just to keep it easy. So there's only constant amount of time per recursive call. Well, we make n recursive calls. So therefore, also the time to combine the solutions, which was that addition, so it's constant time. So this runtime, the algorithm is linear time. So we reduce it from exponential time down to linear time just by storing the values. It's unbelievable how much difference that is, because we talked about a few times ago the difference between n squared and n log n, and it was many times faster. But that's just n squared and n log n. But here it's 2 to the n and n, which is much, much different. So this is much faster. So we can actually do this a different way, but this is a top-down approach. We start at the top, we compute the nth number, then we recursively go down. But there are other ways where we can go bottom up. We start at the smallest value, which is the first number, then we compute the second, then the third, all the way to the nth number. So in terms of dynamic programming, what you'll see a lot of times is top-down or bottom-up approaches. So in order to solve the top case, we recurse on smaller ones. We keep going until we reach the base cases. So how do we do this bottom-up? What we do is we store n equals 1 and n equals 2 in the table. Then we compute values going upward. This is just details, but the idea is the same. So what's better about this algorithm, the bottom-up one? Well, the thing is, I don't need to do recursive calls, right? I just store in the table and I just keep accessing the last two elements as I go. There's no recursion. But we can even improve this even more. I don't need to store anything but the last two values I computed this way. So I don't even need a dictionary or a list here. I just need to store two values in temporary variables, which I think is really nice. So we can have constant space here and still a linear time algorithm, which is much, much better than what we had before. Any questions about this? All right, so I don't have time for that, but next time I'm going to do a coding demo of this to show you how much of a difference this algorithm really does make, and it's huge. Then we'll go into more dynamic programming. So any questions before tomorrow? All right, I'll see you tomorrow.